Hi, folks. Greetings from self-isolation. I hope that you're all doing well. I'll be back after September 24th, but in the meantime, you're in excellent hands with Mr. Carmichael. I had left things in kind of a bit of a messy state here, so I thought, at least for this first lesson, that I'd sort of pick up and try and put things together. So we've talked about Chapter 7 about bivariate stats, and we've talked about correlation and how correlation is not necessarily causation. There's a funny website around correlation and causation at tylervigan.com called Spurious Correlations. We can go through just a couple of them here. We've got the divorce rate in Maine correlates with per capita consumption of margarine. R is 0.992558. Probably not causation there. What do we have here? Total revenue generated by arcades correlates with computer science doctorates awarded in the U.S. I mean, I don't know. Maybe there is a causation there, but you wouldn't immediately assume it. And then my favorite one, number of people who drowned by falling into a pool correlates with the films Nicolas Cage appeared in, and that's an R of 0.666, but that's still pretty high. Again, probably not causation. We looked at Pearson's correlation coefficient. There was this nasty formula for figuring it out. And we found out that the highest value you can take is 1, the lowest value you can take is -1. Correlation of 0 means there's no correlation. A positive correlation means as one variable increases, so does the other. A negative correlation means that as one variable increases, the other decreases. And then that brought us to trying to make lines of best fit. So we had some people's grades in grade 10 math and science, and we put those pieces of data on a grid, and then different people made lines around them to try and make a line of best fit. This one looks a little bit squiggly here. It's not quite a line. But typically you can't get all the points on the line. You just try and do your best. And we said, well, ideally you would put the mean point on there. You'd take a look at the average of all the x values and the average of all the y values and find their mean. So the mean math mark was 75 here. The mean science mark was 80. And if you go ahead and you try and make a line of best fit, it probably should go through that mean point. And maybe it'll look something like that. I don't know. Mine's kind of squiggly too. When drawing a line of best fit, we want the mean point, which is x bar, y bar. And then we just try and follow the contour of the data trend. And that led us to think about, well, how could you computationally come up with, say, the best possible line of best fit? And one technique is called linear regression or least squares regression. And that's kind of where we left it. We had actually filled in this chart here about late bills and credit scores. But I'd like to pull it back just a little bit here because we skipped over a couple of things for the sake of making one of those linear regressions. So there are a couple of terms here, interpolation and extrapolation. This is when you're estimating values. They're techniques for making predictions with bivariate data. Remember, bivariate just means that there are two variables under consideration. So interpolation uses data within your domain. And the IB would say that this is generally an okay thing to do. With all predictions, you should, I guess you should go with a certain amount of caution. But interpolation, we're just going to say, okay, says the IB. Extrapolation uses data beyond your domain, and it's often considered unreliable because we don't know if the trend will continue. So when babies are born, their head circumferences are tracked and to see if they're on a reasonable growth path. But if you took that head tracking information from, say, 0 to 6 months, and then used it to predict the head circumference of a 70-year-old person, that would probably be weird. It would not continue to grow at the same rate throughout a person's whole life. On page 332, there's a couple of examples. Let's just look at number 2 together real quick. So we won't do all the pieces of this, but it really highlights why we should be nervous about extrapolation. Giraffes are the world's tallest mammal and can grow to a height of 6 meters. This table shows a baby giraffe's height during its first year. So you've got age in months up to 12 months and height going up to 4.14 meters. We could find the mean age of the baby giraffe during its first year. I guess it would be 6 months. We can construct a scatter plot and try and go through the mean point. We could find the equation of the line of best fit. Those are all things that we're going to be able to do better computationally in a minute anyways. But just taking a look at these two here, D and E. If we had a model, could we use it to estimate the height of the giraffe at 9 months? We would say yes. That's interpolation because it's within the extremes of these ages that we're dealing with. From 1 to 12 months, you would find 9 months. So if you had a nice model, you could probably estimate that the giraffe's going to be about 3.5 meters tall after 9 months. Use your equation to estimate the height of the giraffe at 10 years. So you can see, in those 11 months, the giraffe grew a little over 2 meters. Is it going to do that every year for the next 10 years? No way. This model has limits to where it's going to be valuable. And so beyond the data that we have, it would be extrapolation. We're not going to do this. No extrapolation. And that's our kind of simple, hard and fast rule, is that extrapolation should be dealt with caution, or you can just say, it's not really okay. So that brings us to computationally derived linear regression, stuff that tries to use calculations to develop the best possible line of best fit. Linear regression creates a line of best fit based on a method that minimizes the square of the vertical distance between each point and the line. We always do linear regression on our GDC. It's only appropriate if you actually have linear data. And linear regression will go through the mean point. It will still contain that sort of average point. So that doesn't mean a lot just to look at the words. Let's take a look at a picture. What's happening behind the scenes when we do linear regression is that we've got some data points here, and we've got an attempt at a best possible line. So there are data points, and there's a difference between the line of best fit and the actual point. It's this amount right here. So sometimes it's above, sometimes it's below. That's called the residual. It's that vertical distance between the line and any given point. What linear regression does, and we're not going to painstakingly do it by hand, but it takes the square of that distance. So it squares them. That would make it all positive. So there's the square of each of those distances shown geometrically. It's a certain amount of area. And it tries to make the sum of all those areas as small as possible. So it has something to do with vertical distance, and in making that distance, or the square of that distance, as small as possible. We'll come back with the example below, but we'll move on here to the late bills and the credit scores. So last time in class, we actually plotted all these points. I'll just quickly put them on now. There they all are. We can find the coordinates of the mean point that the linear regression is going to go through. And to do that, we just add up all these values and divide by 7, because we have 7 pieces of data. You could take a minute and do that in your calculator. It's going to give us 9.29. And then if we added up the y values, okay, or the credit score values here, I'll use a better color than that. Add them up, divide by 7, and you get 663. So the mean point should go through there. So 9.29 late bills and 663. So we can write that down here, 9.29, 663. And I feel like the IB will be sneaky and somehow ask you about mean points on the final exam. The next question is, does it make sense to perform linear regression on this data? And that's one of the good things about us drawing it out. We can see that all those blue points look very linear. Yes, data looks linear. And we'll probably get a good correlation, something close to either 1 or, I guess, closer to -1 in this case. Data looks linear. Okay. If I were to hand draw a line of best fit, I don't know, I guess it would go through the mean point. I'd kind of guess it looks like that-ish and would continue on. Some are over, some are under. But it's going to look pretty close to those points. Okay, that brings us to actually doing the linear regression in our calculator, finding the equation of this best possible line. So here's what we do to get our linear regression. We're going to press Stat, Edit, to put in some lists. If there's anything in there, you need to clear it out. And then we're going to just put in all our X values. 2, 20, 3, 7, 11, 8, and 14. These were the numbers of late bills. and then the corresponding credit scores. 794, 475, 750. And yes, we did do this last class, but you may have forgotten how, or you may not have brought your GDC. If you don't have your GDC, make sure you get it and get some batteries for it. There's all the data in there. I'm going to quit. I'll press second mode. And then I'm going to go stat, and I press over to the right, and I go down to lin reg ax plus b. I press enter, and it asks me, what's your x list? Now the default's going to be list 1 for x, list 2 for y, nothing for frequency list. We won't bother storing it anywhere, and we just go calculate. And it's going to tell us a bunch of stuff. It says the form of the equations y equals ax plus b, the a value, or the slope, is negative 16.4. The b value, or the y-intercept of a line, is 816. And then the r value is negative 0.989. So that means it's very close to negative 1, it's very linear, and it's got a negative slope. As one variable increases, the other decreases. Let's write that down. So it says let y be the credit score, x be the number of late bills. The equation would be this. Y equals negative 16.4, that was the a value, x plus 816 to 3 sig figs. The correlation coefficient that we saw is negative 0.989. If the correlation coefficient is not coming up for you, then you need to go into catalog, which is second zero, and go down until you see diagnostic on and double tap enter. All right, so now that we have this equation, it seems like a lot of work for nothing. But now that we have it, we can actually predict what would happen for different situations. So if we had 10 late bills, I mean, we could look for a person who has 10 late bills. Oh, there's no one there. But somewhere on this line, it's going to predict a certain y value for someone with 10 late bills. And I can just put it into this equation. Put in 10 for x, that would be negative 16.4. Remember, x is the number of late bills. So if we had 10 of them, plus 816, you could run that through in your calculator, and you're going to get a credit score of 652-ish. Let's see, is that what it looked like on my line of best fit? Yeah, but my line of best fit was just sort of an eyeballed thing, so it wasn't perfect. 16 late bills, same thing. You can go, and I'll switch colors here. You can go and put 16 in for x. So we'd have negative 16.4 times 16, and probably the credit score is going to go down. Okay, if we run that through, we're going to get 554. Not as good. Let's see, 50 late bills. So we could put in 50 for x, except that would be, you guessed it, extrapolation. Okay, that would be beyond what we know about. We know about up to 20 late bills. No, we're not going to do this. No extrapolation. And if you actually run it through, I think it gives you a negative number. So suppose a person has 13 late bills. Will the IB allow us to predict their credit score? Let's see. Is that within our known data? Yeah, we have between 2 and 20. That's fine. So yes, interpolation is okay. Is okay. All right. Interpret the meaning of the gradient of the regression line. So remember, gradient means slope. We've got something that looks like this. Negative 16.4x plus 816. Remember, in a line, we often see it as y equals mx plus b. So the gradient, or slope, they'll use the word gradient. It's annoying. I'm sorry. Is negative 16.4. That really means nothing. But slope is a rate of change. So let's think about this. On these axes, we have late bills, and we have credit score. And slope, straight from grade 10, slope is change in y over change in x. So what are these things measured in? Well, this is credit score in points, or points. And the x's are in late bills. The gradient has meaning. It means that credit score is decreasing because it's a negative slope. At a rate of 16.4 points per late bill. Per late bill. I can just take the S off that and use that late bill that I've already got. So there's meaning there. Okay, and that's what we generated from the linear regression. So we've got this slope. The slope has meaning. There's its meaning in context. Interpret the meaning of the y-intercept, the regression line. So a y-intercept is always y value when x is 0. Is 0. Okay, what is x here? It's number of late bills. So what this is telling us is when the number of late bills is 0, late bills is 0, the credit score is 816, which is very high. Now think about that. Is this an okay thing? It does have that meaning, but it would not be a good thing to do because it would be extrapolation. We only know about between 2 and 20 late bills. So we could also mention that here, that even though we're asked to assign meaning, this is extrapolation. And if we want to just sort of talk about it as a blunt instrument, we're just going to say, not okay. Here comes the trap. Predict the number of late bills for someone with a credit score of 620. And it seems like you should be able to just put in 620 for y and predict x. But generally what we like to do is if we're going to make a prediction for something, we want it to go over here. And we want to be minimizing the squares, the residuals, for the thing that we're looking to predict. So this is not okay. Not okay to predict the independent variable. Predict x from y using a standard, or what we might call a y on x regression. So what are we at right now? What's not okay? It's not okay to extrapolate. It's not okay to predict x from y from this standard regression. Big ideas so far. Linear regression is appropriate if data is linear. Regression line contains the mean point. Interpolation is generally okay. Extrapolation is generally not okay. In a line with an equation y equals ax plus b, a is the gradient, or the slope, and slope has meaning as a rate of change. You can look at whatever you're measuring on your y and x axes to give it some meaning. B is the y-intercept. It's the y value when x is 0. And then the last one is saying that you can't predict x from a y value using these standard y on x regressions. But we will deal with how to do that in a little bit. So before we get to the practice over here, why don't we just make sure that we can do this in our calculators using just a sort of abstract example. We've got these points, 28 and 74, 50 and 52, 68 and 31, 90 and 7. Take 2 minutes, throw that data in your calculator, and find the R value and the y on x regression. You can pause. So I head into my calculator, hit Stat, Edit. I'm going to clear out all my lists. Go to the heading and press Clear, Enter. And then I put in all my data. It's all in there. I'm going to quit, so second mode. I'll press Stat, and then over to the right, and choose LinReg. And so far, it's nothing fancy. X list is L1, Y list is L2. Hit Calculate. And it's going to give me a correlation pretty much of -1 and an equation of -1.09x plus 105-ish. There's that R value to 4 sig figs, -0.9996, and we've got -1.09x plus 105. So if I wanted to predict the y value, say when x is 70, I could just plug in a 70 in for x and see what y is. So let's take a few minutes here and head to page 335, numbers 4, 3, 5, 6, and 8 in that order. I'll briefly put them up on the screen here, but even if you get through one or two of them, you get the hang of doing these linear regressions and subbing in some numbers. Question 4, 3, 5, 6, and 8. At this point, we've done pretty much all we need to do for linear regression. A lot of this is going to be calculator stuff, and a lot of it is just skills-based, being able to put the stuff in and decide whether it's appropriate to make a prediction or not. The only thing we haven't really been able to do is this thing of predicting an x value from a y value. And the way to do that is through what I consider a low-yield nitpicking of linear regression. So usually we do a y on x regression. It minimizes the square of the vertical distance between the points on the regression line. These vertical lines are called residuals, and there's a picture in your book. There are those residuals, there are their squares, we make them as small as possible. We get an equation in the form y equals ax plus b, and that's called a y on x regression. It allows us to predict y values. When we get this and we do the lin reg stuff, we can predict y values. So you might be saying, well, okay, I guess if we can't do the other thing, why don't we just switch x and y? Why don't we just make it like this? X is there, y is there. Make some points and make a line of best fit and look at those vertical things and try and minimize those. That's actually a pretty good idea. The only thing that's not great about it is that it makes us switch where x and y is, and it hurts our brain to think about x being the vertical and y being the horizontal. So another way that we could do the exact same thing was leave them as x and y, and instead of trying to minimize those vertical residuals, we try and minimize some horizontal residuals, the horizontal distance between the line and the points. And that actually is going to give us a different regression. It's basically switching the roles of the variables. So predicting x values would require a subtly different type of regression. We would do an x on y regression and get this weird equation, x equals ay plus b. By doing that, we would be minimizing the squares of the horizontal distances. Your GDC hates this idea. And I kind of hate this idea too, like that the thing that you want to predict should probably be on the y-axis. Why not just relabel everything? But every now and then the IB gets nitpicky on this. Let's be clear that the thing we did before, the y on x regression, that's really the most important one. So your GDC is not a fan of x on y regression. To trick it, we swap the definition of x and y in the calculator. Just to recap, here's the data that we were talking about, and here's the question. Predict the number of late bills for someone with a credit score of 620. So let's go back to that. Predict late bills if credit score is 620. And here's what we're going to do in our calculator. We are going to trick it. Trick your GDC. Trick the GDC. GDC. For your X list, choose L2. For your Y list, choose L1. So we've swapped them in the calculator. And then when we get the equation, swap them again. When we get the equation, we won't consider it to be y equals ax plus b, to be y equals ax plus b. But instead, it will be x equals ay plus b, because we've just switched everything around in the calculator. Now, it would be nice if the calculator would just do the regression differently, but it thinks this is really weird, and I think it's pretty weird too. Okay, so let's try that. I'm back at my calculator. I've put all the data in, which you can do, from the bills and the credit scores. Okay, there they are, just as they were before. So I would like to think of this as x and this is y. Now I'm going to quit. If I want to do one of these weird x on y regressions, here's what I'm going to do. So I press stat, I went over to calc, I'm going to choose linear regression. There's no option for x equals ay plus b. So all I'm going to do is switch the order. So for x list, I'm going to tell it it's list 2. I press second and 2. For the y list, I choose list 1, second and 1. And then I go down and I calculate this. And it's told me a whole different set of values. It's going to be negative 0.595 for the slope. Notice that the r value has not changed. But I switched these. So instead of writing it as y equals ax plus b, it's going to be x equals ay plus b. Let's write that down. We found that a, or slope value, was negative 0.0595, y plus 48.7. I hope this gives us a reasonable number. And once we have it in this form, we can sub 620 for y. It's always going to be, if you're using regression for predictions, that this is the thing we want to predict. And this is the value that we'll put in. So we'll have x equals negative 0.595 times the y value of 620 plus 48.7. And we'll get x is 11.8. Does that make sense? If you have a credit score of 620 that we'd anticipate 11.8 or 12 late bills, it does make sense with the data that we have. So this is to the nearest bill, 12 late bills. So a couple of things before we go to some practice. Number one, this regression right here is not just a rearrangement of the other regression we had, the y on x1. It comes from a different technique. It comes from minimizing those horizontal distances. It's kind of specially designed for predicting x values. We can head to the book, and we'll always have to be aware of which kind of regression are we looking for. If you're predicting y values, it's normal. Okay. If you're predicting x values, you switch them up with the shenanigans that we just did here. More complicated. So maybe we'll just talk through and think through this first one. For 7 different theaters, the table below shows the cost of theater tickets and the number of tickets sold in that theater over the course of a week. So cost is x, tickets are y here. That kind of makes sense. Find the regression line of y on x. That means normal. But it's hard to remember all these terms. To predict how many tickets. Okay, so we want to predict y. We want a y equals 1. This is the thing we want to predict. Normal, regular stuff. So x list is going to be L1. Y list is going to be L2, just like we did earlier in the class. Part B. Find the regression line of x on y and use it to predict the cost of a ticket. So here we're going to predict x. That means switch them up. Just like we did on the most recent question. questions that I want you to take a look at. There's 33. Physics and math. Do physics marks depend on math or math depend on physics? It kind of depends on your perspective. That's why we have these two different types of regression. And then there's another one about distance and visitors. So those two. Good luck with the work, folks, and take care.